A railroad made entirely of wood. Not just the ties and trestles, the rails themselves were wood. Smooth logs cut in half lengthwise and laid flat side up to create a running surface. The wheels rolling on these wooden rails were also wooden, hardwood rims that would wear down to nothing in a few months of use. The cars were wooden frameworks held together with wooden pegs. Even the pins that connected cars to each other were wooden. And the motive power? Horses. One or two horses could pull a car loaded with several tons of logs on wooden rails because the rolling resistance was far less than dragging logs over rough ground. This was logging railroad technology in the 1820s through the 1850s, before steel rails became affordable, before steam locomotives were practical for logging operations. Miles of wooden railroad built in weeks, used for a season or two, then abandoned as the logging operation moved deeper into the forest. The wooden rails would rot away within a few years. The wooden wheels would be discarded when they wore thin. But while they functioned, these primitive railroads moved logs at a scale that wouldn't have been possible any other way. This was how America transported timber before modern technology, with wooden rails, wooden wheels, and horsepower. This was early industrial logging in Pennsylvania, New York, and later in the Great Lakes states, at a time when iron and steel were expensive and steam technology was still developing. The logging operations needed to move large quantities of logs from forests to sawmills or to rivers for floating. The traditional method was dragging logs with ox or horse teams directly over the ground. But this was slow and limited to relatively short distances. Logs would catch on stumps and rocks. The animals would struggle in mud and over rough terrain. The labor of clearing paths was substantial. The need for a better system was obvious. The solution borrowed from mining technology. Coal mines had used wooden railways, called tramways or wagonways, since the 1700s. The principle was simple. Wooden rails provided a smooth surface that greatly reduced rolling resistance. A horse that could pull perhaps half a ton dragging a load over rough ground could pull several tons on a rail system. The efficiency gain was enormous, perhaps 10 to 1. If you could build rails into the forest, you could move 10 times as many logs with the same animal power. Could you really build a functioning railroad using only wood, no iron, no steel? Just logs and timber? Could wooden rails support the weight of loaded log cars without crushing or splitting? And could these primitive systems move enough logs to justify the construction effort? The answer is yes. The evidence exists in descriptions from the era, in a few surviving photographs of primitive logging operations, and in the railroad grades, the cleared level pathways that remain in forests where wooden railroads once operated. Before we get to the construction techniques, you need to understand the logging operations that created the need for these railroads. Because wooden logging railroads weren't built for convenience. They were built because the alternative, direct ground transport, simply couldn't move logs at the volume required by sawmills of the early industrial era. A typical sawmill in the 1830s or 1840s might have capacity to saw 10 to 20,000 board feet of lumber per day. That's roughly the wood from 40 to 80 trees, depending on tree size. Over a year of operation, perhaps 200 working days, the mill would consume 8 to 16,000 trees. These trees had to come from somewhere, and they were getting progressively farther from the mill as nearby forests were cut. By the 1840s, some logging operations were moving logs 5 to 10 miles from forest to mill. At those distances, ground transport became prohibitively expensive and slow. The construction of wooden railroads started with surveying a route. The route had to follow terrain that could be graded to acceptable grades with available equipment, hand tools, horse-drawn scrapers, and black powder for blasting if necessary. The grades needed to be relatively flat because horses had limited pulling power on inclines. A grade of 2 to 3% was acceptable. Steeper than that, and you'd need multiple horses or couldn't load the cars as heavily. The route also had to avoid major obstacles like rivers, swamps, or steep ravines that would require expensive bridging. Once the route was surveyed, the actual construction could proceed quickly. A crew of 20 to 30 men could build a mile of wooden railroad in a week or two under favorable conditions. The work was straightforward but labor-intensive. The first step was clearing and grading, removing trees and brush from the route, leveling high spots, filling low spots. This created a roadbed typically 10 to 12 feet wide, enough for a single track with some clearance on either side. The ties were the foundation of the track. These were logs laid perpendicular to the direction of travel, spaced about 2 to 3 feet apart. The ties didn't need to be uniform. Any logs of roughly the right size would work. Typically, they were 8 to 10 feet long and 8 to 12 inches in diameter. The ties were laid directly on the graded surface or were bedded slightly into the ground to keep them from rolling. For a mile of track with ties every 2.5 feet on average, you'd need about 2,000 ties, 2,000 logs that would otherwise have no commercial value. The rails were the critical component. These were made from straight logs, typically pine or hemlock, split lengthwise to create a flat surface. The technique was to select a log 12 to 18 inches in diameter and as straight as possible. The log would be scored along its length with an axe, creating a guideline. Then wedges would be driven into the end grain, splitting the log into two halves. With skill and luck, the split would follow the grain and create two relatively flat half logs. If the log didn't split cleanly, the surfaces would be smoothed with adzes or broadexes. The selection of logs for rails required experience. The best rail logs were young growth trees that had grown with minimal grain irregularities. The splitting process was skilled work. The log would be scored with an axe along its length. Then wedges would be driven into the end grain to start the split. Additional wedges along the length would progressively open the split. If the split deviated from the scored line, additional wedges could redirect it. The quality of the split determined rail quality. A clean split produced a smooth surface needing minimal work. A poor split required extensive smoothing with adze, perhaps 2 hours per rail. The length of individual rails varied depending on available timber, but was typically 16 to 20 feet, limited by the difficulty of handling longer pieces. A rail 16 feet long split from a log 14 inches in diameter and turned flat side up created a running surface about 7 inches wide. This was adequate for wooden wheels 2 to 3 inches wide in the rim. The rails needed to be wide enough that wheels stayed centered even if they wandered slightly side to side. The flat surface of the split log became the top of the rail, the running surface for the wheels. The rounded side would face down, resting on the ties. The rails were laid along the center line of each tie, creating 2 parallel tracks about 4 feet apart, similar to standard gauge. The rails were attached to ties using wooden pegs driven through holes drilled in both rail and tie. Iron spikes weren't used, too expensive. Wooden pegs worked adequately and cost only the labor of cutting and driving them. The drilling of peg holes was done with augers, hand-powered drills. The auger would drill through the rail into the tie beneath. The hole diameter was typically about 3/4 of an inch for pegs that were 1 inch in diameter. The peg would be driven into the undersized hole, creating a tight friction fit. The peg material was typically hardwood, oak or hickory, that would resist splitting and wear. Each rail-to-tie connection required 1 peg, and with ties every 2.5 feet and 2 rails per tie, a mile of track required thousands of pegs, each one hand-cut, hand-drilled, and hand-driven. The alignment of the 2 rails, maintaining consistent spacing and level, was done by eye and by measurement. Workers would use measuring sticks or ropes to ensure the rails were the correct distance apart. They'd use levels or water levels to ensure the rails were at the same height. Poor alignment would cause derailments. If one rail was higher than the other, wheels would climb off the lower rail. If the spacing varied significantly, the car axles would bind, or the wheels would come off the rails entirely. The joints where rail sections met required special attention. A simple butt joint where 2 rail ends met square created a vertical step that would cause jarring and potentially derail cars. The solution was scarfing, cutting both rail ends at a long angle so they overlapped when laid end to end. The scarf might be 2 to 3 feet long, the rail ends cut at a very shallow angle. When overlapped and pegged to ties, this created a gradual transition that wheels could roll over relatively smoothly. The scarfing was done with hand saws and required careful measurement to ensure both ends matched properly. The rail ends were the weak points in the system. The constant pounding of wheels passing over joints would loosen pegs and cause rails to shift. Some operations used iron plates bolted across joints to strengthen them, a compromise between all-wood construction and the expense of iron rails. These joint plates were perhaps 2 feet long and 4 to 6 inches wide, bolted through both rails where they joined. This helped, but added cost, and required imported iron hardware. The rail ends where 2 rail sections met were a challenge. A simple butt joint, 2 rail ends meeting, created a gap that would cause bumping and potentially derail cars. The solution was to cut both rails at a long angle, a scarf joint, so the ends overlapped. This created a smoother transition. The scarfed ends would be pegged to the same tie or to adjacent ties. Even with careful scarfing, there would be some unevenness where rails joined, causing a characteristic bumping as cars rolled over the joints. The wooden rails had obvious limitations. Wood isn't as hard as iron or steel. The wheels rolling over wooden rails would compress and wear the wood. High points would wear down. Low spots would develop where wear was greatest. The rails would also check and split from weather and stress. A wooden rail might last 6 months to 2 years before it was so worn and damaged it needed replacement. This constant maintenance and replacement was accepted as part of operating a wooden railroad. The wheels for cars on wooden railroads were also wooden. The technique was to cut discs from hardwood logs, oak, hickory, or maple. The disc might be 18 to 24 inches in diameter and 4 to 6 inches thick. A hole would be bored through the center for the axle. The rim, the part that contacted the rail, would be left square or slightly rounded. These wooden wheels would wear down from friction with the rails. A wheel might wear down an inch or more in diameter over a season of use, eventually becoming too thin to function and requiring replacement. The construction of wooden wheels was specialized work. The ideal wheel blank came from dense hardwood. The blank would be cut, shaped into a circle, and smoothed. The center hole had to be precisely drilled for the axle. The rim could be square or slightly rounded. Rounded rims distributed load better and wore more evenly. The wear was problematic. A new 24-inch wheel might wear to 22 inches in 3 months. At 20 inches, it would be too small and required replacement. Operations kept spare wheels and tracked usage to replace before failures. The axles were typically wood as well, though sometimes iron axles were used if available. A wooden axle would be a hardwood shaft, perhaps 4 inches in diameter and 6 feet long enough to span between the 2 wheels with some length extending beyond each wheel. The axle ends would be shaped to fit the wheel hub holes. Some axles were cylindrical, the same diameter throughout. Others were tapered, slightly smaller at the ends than in the middle. The attachment of wheels to axles varied by design. Some wheels were fixed to the axle. The axle rotated with the wheels, and the whole assembly rotated in bearing blocks attached to the car frame. And other designs had the wheels free to rotate on the axle. The axle was fixed to the car frame, and the wheels rotated around it. The fixed wheel design was simpler to build but wore the bearing blocks more. The free wheel design was more complex but distributed wear differently. The bearing arrangement was critical to reducing friction. The axle ends rested in bearing blocks, wooden blocks with U-shaped or V-shaped notches cut to cradle the axle. The bearing surface, where the axle contacted the block, had to be smooth and properly shaped. Some operations lined the bearing blocks with leather or fabric soaked in grease to reduce friction. Others used copper or brass bearing surfaces if metal was available. The simplest designs used unlined hardwood bearing surfaces and relied on liberal greasing. The lubrication of bearings was essential. Without lubrication, wooden axles and wooden bearings would generate tremendous friction and heat, potentially setting the bearings on fire. The lubricant was typically animal fat, tallow or lard, or pine tar. These greases would be applied liberally to the bearing surfaces. The grease had to be replenished frequently, typically daily or after every few loaded trips. A worker called a greaser would have the job of applying grease to all bearing points on all cars at regular intervals. The maintenance of wheels and axles was constant work. Wheels had to be inspected for cracks, splits, or excessive wear. axles had to be checked for damage or misalignment. Bearing blocks had to be examined for wear and re-greased. The frequency of inspections depended on usage intensity, but might be daily for heavily used cars. The replacement of worn components was done during downtime, typically overnight when cars weren't operating. The cars themselves were simple wooden frameworks. A typical log car had two axles about 6 feet apart, connected by a wooden frame. The frame was just heavy timbers bolted or pegged together to create a rigid structure. There were no sides or ends, just the frame that logs would rest on. The car might have stakes that could be inserted to keep logs from rolling off, or chains to secure the load. The entire car might weigh a few hundred pounds unloaded and could carry several tons of logs, perhaps 10 times its own weight. The coupling between cars was primitive. Some systems used wooden pins through matching holes in the car frames. Others used chains or rope. The important thing was that the coupling allowed one car to pull another, creating trains of multiple cars behind a single horse or team. A horse might pull 3 or 4 loaded cars on level track, though on grades they might pull only 1 or 2. The horses used for this work were draft animals, large, powerful horses bred for pulling heavy loads. A good draft horse might weigh 1,600 to 2,000 pounds and could sustain a pull of about 10% of its weight, 160 to 200 pounds, for extended periods. On wooden rails, this was sufficient to move several tons of logs. The horse would be hitched to the front car and would walk alongside the track, pulling the train of cars. A handler would walk with the horse, controlling speed and direction with voice commands and reins. The operation of a wooden railroad was straightforward, but required coordination. Empty cars would be pulled into the forest to where logs were being cut. The logs would be loaded onto the cars using horses or oxen with chains and simple lever arrangements. Once loaded, the car or train would be pulled back to the sawmill or to a landing where logs would be unloaded. The unloading was typically done by simply tipping the car. The car frame would be constructed so it could rotate on the axles, dumping the logs off to one side. The empty cars would then return to the forest for another load. The loading process required both equipment and technique. The logs being loaded were large and heavy, perhaps 12 to 24 inches in diameter and 12 to 16 feet long. A log of this size might weigh 500 to 1,500 pounds. Moving such weights required mechanical advantage beyond human muscle power alone. The standard technique used a loading ramp and animal power with chains or cables. The loading ramp was a simple incline structure built beside the railroad track. The ramp would slope from ground level up to the height of the car bed, perhaps 3 to 4 feet of vertical rise over 10 to 15 feet of horizontal distance. The ramp surface would be smooth logs or planks. A log would be positioned at the bottom of the ramp. A chain would be wrapped around one end of the log. A horse or ox would be hitched to the chain. As the animal pulled, the log would drag up the ramp onto the car. The technique required a worker to guide the log with a peavey or cant hook, lever tools designed for rolling and positioning logs. The positioning of logs on the car required care. The logs had to be arranged so their weight was balanced, roughly equal weight on each side of the car center line and roughly equal distribution front to back. An imbalanced load would cause the car to tend to tip or would put uneven stress on wheels and axles. Some operations use standards, vertical stakes inserted into holes in the car frame to keep logs from rolling off. Others relied on careful stacking and perhaps chains or rope to secure the load. The number of logs per car load depended on log size and car capacity. A car might carry 3 to 6 large logs or 8 to 12 smaller logs. And the total weight of a loaded car might be 3 to 6 tons, several times the weight of the car itself. This weight stressed all components of the car and track system. The wheels would sink into wooden rails, creating compressions that became permanent deformations. The axles would flex under load. The car frame would creak and strain. The movement of loaded cars required proper horsepower. A single horse could pull 1 or perhaps 2 loaded cars on level track. On grades, even a single loaded car might require 2 horses. The standard practice was to hitch the horse directly to the front car with traces, the leather or rope harness elements that transmitted pulling force. For multiple car trains, the cars would be coupled together with chains or pin and hole couplings. The horse would pull the entire train, and with each car's rolling resistance and momentum affecting the others. The control of loaded trains required skill from the horse handler. On level ground or gentle downgrades, control was straightforward. The horse provided motive power, and the handler controlled speed with voice commands. But on steeper downgrades, gravity would tend to pull the loaded train downhill faster than was safe. The handler had to use braking techniques to control speed. The simplest brake was a wooden block or pole that could be jammed against a wheel to create friction. More sophisticated cars had simple brake shoes that could be pressed against the wheels or rails. The unloading at the sawmill or landing was designed for speed and simplicity. The simplest unloading technique was the tip car. The car frame was designed to pivot on its axles. When the coupling to other cars was disconnected and any holding pins were removed, the loaded side of the car could be lifted with levers, tipping the frame and causing logs to roll off. The tipping required several workers with long pry bars to lift one side of the frame. Once tipped beyond the balance point, gravity would complete the rotation and logs would tumble off. The empty frame could then be leveled and was ready to return to the forest. More sophisticated operations used unloading ramps, essentially the reverse of loading ramps. The car would be positioned alongside a ramp. Workers would roll or push logs from the car down the ramp to ground level. This was slower than tipping, but allowed more control over log placement and reduced the impact forces on the logs themselves. For high-quality logs destined for special uses, the controlled unloading prevented splitting or damage that might occur from tumbling logs off tipped cars. The daily production of a wooden railroad depended on many factors: the distance from forest to mill, the terrain, the number of cars and horses, the efficiency of loading and unloading. A well-organized operation might move 50 to 100 tons of logs per day, perhaps 200 to 400 logs of usable size. This was several times what could be moved by direct ground hauling with the same labor and animal power. The cycle time for a complete trip, loading in forest, hauling to mill, unloading, returning empty, determined daily capacity. If the forest cutting area was 2 miles from the mill, a round trip might take 2 hours, including loading and unloading time. With a 10-hour working day, a single horse and car set could make 4 or 5 trips. If each trip moved 6 logs, the daily total would be 24 to 30 logs per horse and car combination. With multiple horse teams operating, the daily total could reach substantial numbers. The coordination between cutting operations and railroad operations was essential. The loggers cutting trees had to work ahead of the railroad, keeping a supply of felled logs ready for loading. If the railroad crew arrived and no logs were ready, they'd wait idle while loggers scrambled to prepare loads. If logs were cut but not loaded promptly, they'd accumulate and clog the operation. The efficient balance required communication and scheduling between the forest boss supervising the cutters and the railroad boss supervising the trains. Among the workers who operated wooden railroads was a man named Samuel Brown, who worked in Pennsylvania logging operations from 1835 to 1858. Brown's account was recorded in an interview published in a lumber trade journal in 1872 when he was elderly. His descriptions provide insight into how these systems functioned. According to the interview, "I worked on the wooden railways we built into the forests. The rails were split pine logs laid flat side up. The wheels of the cars were oak, perhaps 2 feet across. We would build a mile of railway in a week with a good crew. The building was not difficult. Lay ties, peg down rails, and you have a railway. The maintenance was constant. The rails would check and split. Wheels would wear down and need replacing. But the railway allowed us to bring out 10 times the logs we could haul on the ground." Brown described the operation. A horse would pull 3 or 4 cars loaded with logs. The horse walked beside the track, not on it. The handler walked with the horse. We could make 4 trips per day from the cutting area to the mill, 5 miles round trip. Each trip might bring 12 to 16 logs. In a day, a single horse team could deliver 40 to 60 logs. We had 6 teams operating, so perhaps 300 logs per day reached the mill. Without the railway, we might have moved 30 or 40 logs per day with all the horses working to drag logs on the ground. Brown also described problems. The greatest problem was derailment. If a wheel hit a bad spot in the rail, or if the load shifted, the car would come off the track. Then we had to stop everything and lift the car back on. This might take an hour with multiple men and pry bars. Derailments happen perhaps twice per day. We accepted this as part of the operations. The other problem was weather. Rain would make the wooden rails slippery and swollen. Frost would make them uneven. In winter, snow and ice made operation nearly impossible. The railways worked best in dry weather. Brown described additional challenges. The maintenance of the railway was constant. The rails would check and split from sun and weather. We would have to replace sections of rail perhaps once per month. The wear from wheels was concentrated at certain points, where the railway curved slightly, where grades changed. At these points, the rails would wear into grooves an inch deep within a few weeks. We would try to shift the rails slightly to present fresh surface to the wheels, but eventually the rail was so worn it had to be replaced entirely. Another documented worker was James McCready, who operated a wooden railroad in New York State from 1842 to 1854. McCready's diary, preserved in a local historical society, provides detailed observations about costs, production, and the transition from wooden to iron rails. From his diary, June 1845. We have completed construction of 2 miles of wooden railway from the sawmill into the timber tract. The construction required 6 weeks with a crew of 20 men. The costs were as follows: labor for grading and construction, $800. Timber for rails and ties, no cash cost, as we used our own timber, not suitable for sawmilling. 6 logging cars constructed, $240. 4 draft horses purchased, $600. Harness and equipment, $160. Total investment approximately $1,800 for the railway and equipment. McCready documented production. In the first month of operation, we moved approximately 3,000 logs. This is triple what we moved previously using ground hauling. The railway has proved its worth. However, the maintenance requirements are substantial. We must inspect rails daily and replace damaged sections weekly. We have already replaced approximately 300 feet of rail, nearly 15% of the total length, in just 1 month of operation. A later entry from 1848 describes maintenance in detail. The railway requires constant attention. The greatest wear occurs at 3 locations. First, where empty cars are loaded, the repeated stopping and starting of heavy loads compresses and damages rails. Second, at the mill yard where logs are unloaded, the impact of tipping cars drives rails into the ties. Third, at grade changes where the track changes angle, the wheels pound these transitions severely. At these locations, we now replace rails monthly. In other sections, rails last 3 to 6 months before wear requires replacement. McCready's 1850 entry describes a major investment decision. I have purchased iron strap rail, iron plates 3 inches wide and 1/4 inch thick in 16-foot lengths. We are spiking these iron straps to the top surface of our wooden rails. The iron provides a much harder wearing surface. The cost is substantial. $2 per linear foot of track for the strap iron and spikes, which means $800 for our 2-mile railway. But I calculate the iron straps will last 5 years or more, eliminating the constant wooden rail replacement that has cost us at least $200 annually. The investment should repay itself within 4 years. A final entry from 1854. We have completed replacement of our wooden railway with full iron rail. The total cost was approximately $6,000 for rails, spikes, and additional grading to handle the heavier loads that iron rails permit. We can now operate steam locomotives rather than horsepower. The locomotive cost $4,000 but can move 10 times the logs per day that our horses moved. This railway has transformed our operation. We now produce 30,000 board feet of lumber per day, triple our production before the iron rails. The wooden railway served us well for 9 years, but iron is clearly superior in every way except initial cost. The maintenance challenges of wooden railroads extended beyond rail replacement. The ties would settle unevenly into the ground, creating dips and bumps in the track. Workers would have to dig out settled ties and shim them with rocks or wooden blocks to restore level track. The ties themselves would rot, especially in wet areas, requiring replacement. A tie that rotted through would no longer support the rail adequately, allowing the rail to sag or shift. The seasonal variations in weather created specific problems. In spring, snowmelt and rain would saturate the ground, causing ties to sink into softened earth. The rail would follow the tie, creating dips that collected more water, accelerating the deterioration. In summer, the wood would dry and shrink, causing rails to separate at joints and ties to work loose from their pegs. In fall, falling leaves would coat the rails, making them slippery and reducing traction for wheels. In winter, frost would heave the ground unevenly, throwing track out of alignment. The repair of derailments was a common and time-consuming task. When a wheel came off the rail, the entire car had to be lifted to get the wheel back on track. This required jack screws, pry bars, and multiple workers. The process might take 30 minutes to an hour, depending on the situation. If the derailment occurred on a grade or curve, the task was more difficult because gravity or momentum had to be overcome. Some operations kept repair equipment positioned at problem locations where derailments were frequent. Another documented operation was in New York State in the 1840s, described in company records preserved in a historical society collection. The records show the costs and production of a wooden railroad built to serve a sawmill operation. The railroad was approximately 4 miles long and cost about $3,000 to construct, equivalent to about $90,000 in modern currency. This included labor for grading and construction, materials for rails and cars, and the purchase of 6 horses. The production records show that the railroad moved approximately 30,000 logs in its first year of operation, an average of 150 logs per working day. The mill processed these logs into approximately 6 million board feet of lumber. Without the railroad, the company estimated they could have produced perhaps 2 million board feet, a threefold increase in production from the railroad. The railroad paid for itself in increased production within less than 2 years. The decline of wooden railroads came with the availability of iron and steel rails. Iron rails were introduced in the 1830s and became increasingly common in the 1840s. Steel rails became available in the 1860s. Both were superior to wooden rails in every way except cost. They were harder, more durable, and created a smoother running surface. An iron rail might last 10 to 20 years compared to 2 years for wood. A steel rail might last 50 years or more with maintenance. But iron and steel were expensive. In the 1840s, iron rails might cost $50 to $100 per ton. A mile of track required perhaps 30 to 40 tons of rails, meaning $3,000 to $4,000 just for the rails, equal to or greater than the entire cost of building a mile of wooden railroad, including grading and labor. For small logging operations with limited capital, wooden rails were the only economically feasible option. The transition period from the 1840s through 1860s saw hybrid systems. Some operations used wooden rails with iron straps spiked to the top for a wearing surface. The strap rail was cheaper than solid iron rail, but more durable than wood. The iron strap would wear, rather than the wooden rail beneath it. When the strap wore thin, it could be replaced without replacing the entire rail. Strap rail was common in early American railroading generally, but was particularly useful in logging operations where capital was limited. The introduction of steam locomotives to logging operations required iron or steel rails. The weight of a locomotive, perhaps 10 to 20 tons, even for a small logging engine, would crush wooden rails. The heat from the locomotive firebox and smokebox created fire hazard with wooden track, and the greater speeds possible with locomotives, 10 to 15 miles per hour, required the smooth, uniform surface that only metal rails could provide. As steam locomotives became practical for logging in the 1870s and 1880s, wooden rails became obsolete for operations of any significant scale. But wooden railroads continued in use in some isolated operations into the early 1900s. Small sawmills in remote areas might build short wooden railroads because they couldn't afford iron rails and didn't need the capacity that justified the investment. These late wooden railroads were anachronisms. throwbacks to an earlier era of technology used where nothing better was available or affordable. The archaeological evidence of wooden railroads is minimal because wood decays. The rail beds, the graded paths through forests, sometimes remain as linear features visible a century or more later. These old grades can be followed through forests where they appear as level pathways unnaturally straight given the terrain. But the rails, ties, and other wooden components are long gone, rotted away within years or decades of abandonment. The legacy of wooden railroads is their role in the transition from pre-industrial to industrial logging. Before wooden railroads, logging was limited by animal power applied directly to dragging logs. The introduction of rails, even wooden rails, multiplied the effective power of animals by reducing friction. This enabled larger-scale logging operations that could supply growing sawmill capacity. When iron rails and steam locomotives arrived, they built on the foundation created by wooden railroads, using the same basic concept of rail transportation, but with materials and motive power that could scale to far larger operations. The workers who built and operated wooden railroads, men like Samuel Brown and hundreds of others whose names weren't recorded, were part of the technological transition from animal power to mechanical power. Sure, from local to industrial scale operations, from traditional crafts to modern engineering. They worked with the technology available to them, wood, horses, hand tools, and made it functional. The wooden railroads they built were crude by later standards, but represented significant innovation at the time. The economics of wooden railroads illustrate the relationship between technology, capital, and development. Wooden rails were chosen not because they were superior, but because they were affordable. When better technology became available at acceptable cost, wooden rails disappeared rapidly. This pattern, using inferior but affordable technology until better technology becomes accessible, repeats across industrial history. The wooden railroad era was brief, perhaps 40 years from first use to obsolescence, but during that period it enabled logging operations that wouldn't otherwise have been practical. The engineering challenges of wooden railroads seem simple in retrospect, but were significant at the time. How do you create a rail that's straight enough, strong enough, and wear-resistant enough to function? How do you join rail sections smoothly? How do you design wheels that will roll on wooden rails without crushing them? How do you prevent derailments? How do you handle grades and curves? These problems had to be solved through experimentation and experience. The solutions that emerged, scarf joints, hardwood wheels, gentle grades, careful grading, represented accumulated practical knowledge. The social organization of wooden railroad operations required coordination between different groups of workers. Loggers cutting trees in the forest, workers building and maintaining track, horse handlers operating the trains, mill workers processing the logs, all had to work together for the system to function. The wooden railroad was infrastructure that connected these groups and required them to coordinate their activities. This organizational challenge was as significant as the technical challenge of building the railroad itself. The environmental impact of wooden railroads was relatively minor compared to later logging operations, but still significant. The rail bed required clearing a swath through the forest. The trees used for ties and rails, though not of commercial lumber quality, still represented forest removal. The concentration of traffic on rail lines created compacted, disturbed corridors, and the logging operations enabled by the railroads removed far more trees than would have been cut otherwise. The wooden railroads were tools that enabled larger-scale environmental modification. The documentation of wooden railroads is sparse because they were considered unremarkable at the time. Newspapers didn't write articles about logging railroads. Company records, if they mentioned railroads at all, might note them as line items in cost accounting. The detailed technical information about construction and operation exists primarily in scattered accounts like Samuel Brown's interview and in occasional descriptions in lumber trade publications. Historians have had to piece together the wooden railroad story from these fragmentary sources. It's the comparison to European practice shows different technological trajectories. European logging operations in the same era more commonly used water transport. floating logs in rivers, or invested in iron rails earlier because capital was more available and forests were more valuable. The American pattern of wooden railroads reflected both the abundance of wood and the scarcity of capital in a developing economy. Americans used what they had, wood, because iron was too expensive to import or manufacture domestically in sufficient quantity. The memorial to wooden railroads and their builders is the forest itself, or rather the absence of the forests that were cut using these primitive transportation systems. The logs moved on wooden rails became the lumber that built American cities in the mid-1800s. Philadelphia, New York, and Boston, the buildings in these cities from the 1830s through 1860s, were built partly with lumber transported on wooden railroads. The connection between primitive wooden rails and sophisticated urban architecture seems unlikely, but is historically real. Today, if you know where to look, you can find remnants of old railroad grades in forests throughout Pennsylvania, New York, and other early logging regions. These level pathways through terrain that otherwise has no level paths are the ghosts of wooden railroads. The rails are gone, the ties are gone, the cars and horses are gone. But the cleared, graded pathway remains, showing where horses once pulled trains of logs on wooden rails. That's the physical legacy of wooden railroad technology, linear scars through forests, mostly healed over but still detectable a century and a half later. Wooden rails, wooden wheels, wooden cars, horses for motive power, it sounds impossibly primitive. But for a few decades in the early and mid-1800s, this was cutting-edge technology for log transportation. It multiplied the effective power of animals tenfold. It enabled sawmills to expand production threefold or more. It was the intermediate step between pre-industrial and industrial logging. And it worked, which is all that mattered at the time. The lumber that built mid-19th century America rode on wooden rails pulled by horses. And that's worth remembering as part of the technological history that shaped the modern world.